Okay, good morning. Can you hear me okay? Hopefully today we don't have issues like we did yesterday. Apologies, I'm guessing it's just internet traffic that is absolutely crazy everywhere. So to recap, we were talking about the most important monosaccharides we need to be aware of. So we talked about glucose, several myths out there. Dextrose is a common name. You may see this when you work in the clinic. Patients will be given a dextrose solution, which is pretty much a glucose solution, different combinations that are out there depending on what the patient is going to need. As we mentioned, glucose, critically important nutrient for all cells in the body. It's the primary energy-producing monosaccharide in all in biochemistry. It's exergonic metabolism that it provides energy for other multiple reactions that we're going to be learning. We'll talk about metabolism later. Some of those reactions require energy. They are exergonic processes. Then the glucose being metabolized will provide the energy for those multiple types of organic biochemical processes. As we mentioned, it's also an important building block for all kinds of larger complex carbohydrates. It is one of the primary components of glucose, components of sucrose, and then it also is going to be one of the components of glycogen, which is a polymer that provides energy to the body between meals when we're to provide cells with glucose and we're not having a meal glucose coming from the diet from a meal. And then it's also an important plant product when we ingest carbohydrates from the diet. The starches that come from the diet, of which there's different kinds of that we call digestible saccharides. Also what we call cellulose, which what ultimately is what we call important component in the diet. All of that is composed of glucose. So when you're looking at the structure of glucose, remember in the chain form, it's right, left, right. The next one to the right is what defines the L version of the sugar, and what ultimately will combine with this carbon to form the ring structure. But when you're looking at the other are labeled in right, left, right, down, up, and down in ring structure. And then the blue one, that's the CH2, the OH pointing to the right, which is what defines an a D sugar, that ultimately translates to this CH2OH pointing upward. And as we've discussed, there's two versions of the ring form. There's the beta version shown here, and then there's the alpha version at the bottom. So both of them indicated in this slide. We also talked about lactose. There's one difference with glucose and one that's highlighted in red in the red square over here. They differ on carbon number 4. What that means is that in the root form, carbon is the one highlighted there. So if you notice, down, up. Again, my lord. Hold on. Let me try this thing off. If it works without my head. Can you hear me now? Is that better? Yes, okay. All right, so we're good. There was an issue here with the mic. I think we're okay now. Sorry about that. All right, so again, back to galactose. The difference between glucose and galactose is, let me just make sure the recording is on, and it is, okay. The difference between galactose is this sugar here on carbon number 4, which then travels to the hydroxy on the ring being pointing upward in that position. Again, right, left, left means down, up, up. If you go back to glucose, right, left, right means down, up, down. So the difference is here, it's in the opposite direction, and that's why then this one is going to be pointing upward. And again, this here would be, in this case, this is the alpha because it's in the same direction. This here is the beta because it's in the, sorry, the first one is in the opposite direction. Beta is in the same direction. So this is where we were going to start today. We've already spent 8 minutes with this business here with the internet and whatnot, but we're fine. So fructose is the major ketose that exists in nature. I'm going to zoom in just a smidgen over here so that I can see things a little bit better. So if you look at fructose, the difference again is that there's a ketone in the structure as opposed to an aldehyde. So there's 1, 2, and 3 chirality centers. The furthest one from the ketone is the one that defines this one as a D sugar. So then technically in the ring structure, the 2 that you really need to pay attention to would be these 2 that would translate to, if you notice, this is to the left, which means it's going to be upward in the ring. Notice it here. And then this one's to the right, which means it's going to be down in the ring. So in similar fashion as you would do with the aldoses, again, the hydroxy group that defines that it's a D sugar would wrap around and form a bond to the ketone, because the ketone is 1 carbon in. When you can, let me go back, when you compare that with glucose and galactose, the aldehyde is at the very end, right? And when this forms a bond with this, it results in a 6-membered ring. Because the ketone in fructose is on this position, on position number 2, it's technically, the ring is 1 carbon short when this ultimately wraps around and forms the bond with that. Remember, I keep saying the analogy, imagine your hand touching your feet and grabbing your toes, and that's the ring. Well, in the case of a fructose, it's your hand latching onto your knee. It's a little bit shorter, makes the ring a little bit smaller, right? And therefore, what you end up with is a 5-membered ring. Back to the open chain compared to the closed chain, left, right, immediately after the ketone means up, down. This carbon that I'm highlighting here in blue is the ketone carbon. That's the one where the OH shown with the arrow going up, that's the one that is wrapping around. Again, I'm gonna circle this, that's this oxygen over here. And again, this carbon is the ketone carbon to which the ring has latched onto. So if you notice, the CH2OH on the furthest most chirality center, which is this here, this corresponds to this, pointing upward, just like with glucose, that's what means that this is a D sugar. And then the hydroxy that results on carbon, which is now number 2, sorry, not this one, the ketone, the one that I was highlighting in blue here that I'm now overwriting in red, the fact that this is upward, this hydroxy, they're in the same direction. This is the beta form of the sugar. Notice the name, beta. If that ketone rotates, same principle as before, and it's caught by the hydroxy with this pointing downward, then you end up with, this is D, this hydroxy is in the opposite direction. This is the alpha form of the sugar. So the same principles will apply. You just have to stand back and look at it in the perspective of the alternative sugar. Let me simplify this so that you can see it a little bit better, right? So this is what makes it D. This is, again, what makes it D. The fact that this is down, this is what makes it alpha. And if you follow, left, right means up, down. Notice, up, down, up, down, up, down. Okay, so this is fructose. When you see a 5-membered ring, it's going to be fructose. So fructose is a very important sugar in our diet. It comes from all sorts of sources, contained in very large amounts in all kinds of fruits and things of the sort. This is why it's called fructose. It derives from fruit sources. Turns out that about 40% of honey is pure fructose, and fructose is actually sweeter by about 75%. We're going to talk about different carbohydrates and their level of sweetness. You're also, if you've taken the lab already on carbohydrates, you would have learned that there's different sugars out there and they have different levels of sweetness. So it turns out fructose is much sweeter than sucrose and glucose. So this is why honey is sweeter than regular table sugar or glucose per gram, because the sugar itself is much sweeter. You probably have heard of high fructose corn syrup, used for the past several decades in as a sweetener in sodas and even like artificial Aunt Jemima syrups and things of the sort. It's because you can actually, and this shift happened several decades ago, it's because per gram you can use much less fructose than you need sucrose to sweeten these foodstuffs, and therefore it's an enormous cost savings for the manufacturers of these products. Of course, we learn after the fact that there's issues related to health concerns related to high fructose. It's unclear as to the reason why, because fructose is actually an important metabolite, but there's been associations between high levels of ingestion of fructose as opposed to just regular sucrose. And again, it's an issue, right? So you probably have seen many sodas and many products are now shifting back to regular sugar as opposed to having high fructose corn syrup in their content. So there's a series of very important sugar derivatives that exist in nature, which many of them have particular roles in biochemistry, and we're going to see several of them in different places, but we're now going to introduce their structures because they end up having very important functions in biological systems. So they're sort of listed here. We're going to be going through the examples of what they are so that you can then learn to visualize them, and it's going to become very important for you to be able to recognize them. So we already started to briefly allude to deoxy sugars. These deoxy sugars are missing oxygen. Deoxy means missing oxygen. So it turns out that they're missing at least one, if not several, of the hydroxy groups that make up the sugars. Remember, sugars are aldehydes or ketones with several alcohol, i.e. hydroxy groups scattered throughout. If they're missing at least one, it can be more than one, they're called deoxy sugars. There are other types of sugars in which an amino group, NH2, or a derivative of an amine, is replacing one or more of the hydroxy groups. So these are called amino sugars, and there's several amino sugars that are critically important in particular places that they serve very specific functions, and the body utilizes them accordingly. And then we have oxidized or reduced versions of sugars, which again play different roles in different locations. If you recall the discussion that we had about bilirubin and newborn babies and their liver being unable to completely get rid of the bilirubin byproduct that comes from the breakdown of red blood cells, we talked about how the bilirubin needs to be conjugated with sugar derivatives that are highly polar. It turns out that it's these oxidized sugars in the form of carboxylic acids that are critically important in being attached to these very non-polar substances. This not only happens during metabolism, it also happens when you're exposed to toxins coming from all kinds of infectious agents and all kinds of sources of exposures to toxins and poisons. Many of these substances are actually non-polar, and the body, the liver in particular, because that's one of the major jobs of the liver, is detoxification, will attach these highly polar carboxylic acid sugars, which are very water soluble. they will attach them to these entities, and that's one way to make the entities very water soluble so that then your kidneys can get rid of them. And that's a major mechanism for detoxification. And then there is a series of sugars that are out there that we call reduced sugars. We also call them alcohol sugars, because what happens is that the aldehyde or ketone that the sugar originally was carrying has been reduced to an alcohol. Okay, we're going to look at pictures and you're going to see what I'm talking about. And then we call them reduced sugars. These are not as critically important in biochemistry. There are not that many examples of these reduced sugars in biochemical systems, not as much as the carboxylic acid sugars, but they've actually become a major commodity in the food industry, particularly targeting diabetics who are unable to ingest high levels of sugars. They have to limit how much sugar they ingest. These reduced sugars actually are used as food additives. They provide the taste of sweetness, but they're not absorbed and they're not metabolized in the same way as regular sugar is, and therefore what we call the glycemic index, how much your sugar, your blood sugar spikes after a meal, is much less, it's much less intense, or it's much reduced, for lack of a better word. With these alcohol sugars, so these individuals who are diabetics can ingest these sugar-free cookies and sugar-free chocolates that you may find in different places. It turns out the sweetener that's in them, and these are just a handful of a whole bunch of products that are out there. These are the sweeteners that are in them that are sugar-free. It's because they have these substances that give you the taste of the sweetness without providing the spike in blood sugar. Now, ever tried these products? They actually have a little bit of an aftertaste, because these substances, yes, they provide sweetness to a certain degree, but they also have, you know, because they're different than the original sugar, they trigger your taste buds in a different way, and they provide sometimes a bitter like aftertaste. So here's some examples of some of these substances that I've been speaking of. So here, for example, is the deoxyribose. We mentioned this previously. Here you have a hydroxy group that's missing from this structure. And then if you notice, here are the ring versions of the same compound. Notice this is the chirality center that's furthest from the aldehyde, because this one itself is a 5-carbon sugar. When this wraps around, it will form a 5-membered ring. And again, you only have one chirality center to be concerned with in this particular case, because this one is missing a hydroxy. To the right means that it's down. Notice this is pointing up, so this is D. Notice this is D. And then this hydroxy here is pointing downward. This is the alpha version of the sugar. This is pointing upward. This is the beta version, and you can see it right here. Okay? If you look at the bottom, there's a sugar that is at the furthest most chirality center. There's a hydroxy that's to the left. So this is actually an L sugar. It's called L-fructose. And this fructose is, not only is it L, but if you notice, I'm going to use a different color, the furthest most carbon, not the furthest most chirality center, but the furthest most carbon, which in most sugars is CH2OH. Notice how this one is missing the hydroxy group from that position. So here's a very good example of what I've been talking about regarding the definition of alpha versus beta. So again, if you noticed, left, right, right, in this case means, well, as is the other case, it means up, down, down, okay? However, if you notice, because this is an L sugar, the what would be the CH2OH, which in this case is a CH3, notice how this is pointing downward. So downward means that it's L, right? Upward means that it's D, as in the one above. So this is an L sugar. And now if you observe, let me change colors again. This hydroxy is pointing downward in the same direction as the CH3. So this is the beta version of the sugar. So as I kept saying, alpha versus beta doesn't mean that this is down versus this is up. It means the same direction as the CH2OH or CH3 in this case, because they're both downward. Let me clean this up because it's already getting too messy over here. If you observe, this makes it L, this is downward, same direction. This is what makes it beta. So notice, beta L fucopyranose, okay? Let me just briefly say something about this pyranose issue. Whenever you have a 6-membered ring form of a sugar, they're called pyranoses. Whenever you have a 5-membered ring sugar, they're called furanoses. The reason is there's a compound out there, and I'm going to write the structure. This compound has 2 double bonds. It's called pyran. And then there's an alternative compound that looks like this that's called furan. So because the skeletons of these structures resemble furan and pyran, the 5-membered sugars are called furanoses. The 6-membered sugars are called pyranoses. Okay? If you've been looking at the previous slides that we've been talking about, I hadn't mentioned this before, but here is fructofuranose. It's a 5-membered ring derived from fructose. That one happens to be the beta, and it's also the D. So beta D, fructo, coming from fructose, furanose, it's the 5-membered ring form of the sugar. Okay, that's what that means. If I go back one more, here's the galactose. If you notice on the galactose, this is the beta, this is the D, this is coming from galactose, it's the ring form beta D galactopyranose, because it's the 6-membered ring coming from galactose. So again, I keep stressing there's a lot of minutia, meaning paying attention to detail in this chapter. There's no math, math is gone, right? Somebody asked a question a few moments ago. Let me see what the question is. So if the 2 OH on the topmost and the bottommost are on the same side, we can assume they are beta simply by looking at the Fisher projection alone. Hold on, let me go look at the Fisher projection. OH on the topmost, you mean this one? No? And bottommost, this one. No, it cannot be from the Fisher projection. Beta and alpha only applies to the ring forms. Okay, so let me go back to the slide that I was in, because that illustrates the concepts with different sugars. So in this case, this up means this to the right. These two go together. That's what makes it D. Okay, and then alpha versus beta will ultimately mean once this forms the bond here, which has not happened in the open chain, once this closes, that's what then allows this to be either up or down, right? When these two are in the same direction, it happens to be up here because this is up, that's what defines it as a D sugar. This is beta, right? This is up what makes it D, this down, combined with that is what makes it alpha. In the bottom sugars, both of which are L, this is also a deoxy sugar because it's missing the OH on that bottom carbon. This here is what makes it L, which translates to the CH3 being downward, okay? That's what makes this sugar an L sugar. And because this is downward and this one is upward, they are opposite. This happens to be the alpha form of the sugar. So notice the name. Right? Alpha, because they're opposite. L, because this is to the left, which means this is down. Rhamno, because it comes from rhamnose. Pyranose, because it's a 6-membered ring. Okay? I hope that clarifies that whole thing. All right. So then come the amino sugars. These are the ones that have amino groups substituting somewhere along the skeleton, substituting an OH group. So if you pay attention to this one, this is D, this is beta, and then down, up, down, this comes from glucose. Now, because there's an amino group in the structure, this is not glucose, this is an amino derivative of glucose. So this one happens to be called, if you notice, alpha D, We got that from the ring structure. And then we call it glucosamino because it's a glucose with an amino group on it. And then of course it's a pyranose because it's the 6-membered ring. You can look at it in the open chain form in the center. Notice right, left, right, it's what makes it coming from glucose. This one to the right is what makes it D. So D-glucosamine is the name of the structure because it's a glucose that now has an amine on position number 2. It technically should have been 2D-glucosamine, but there's really not any other glucosamine out there if you look in nature. Now, there are further modifications that nature will do to these amino sugars. And one of the most important modifications that nature will do, in addition to removing the hydroxy and substituting it with an amino group to make it glucosamine, further modification will happen, can happen. And one of the most important ones is the substitution of, or the addition of an acetyl group, right? So acetyl is, if you have any structure and it has a C double bond O CH3, this is called an acetyl group. I wrote it up here. I'll write it again. Acetyl group. Okay? That's a general structure. So this one happens to be called acetyl glucosamine. We call it N-acetyl because that tells the reader that the acetyl group is attached to the nitrogen of the glucosamine. Okay? It's D-glucosamine because of the fact that this is to the right. And these amino sugars that are acetylated, meaning carrying an acetyl group, are actually important metabolites in different places. So if you look at these structures that are shown here, again, just to compare these two, both of these are D. This is alpha, this is beta. They have a amino group and it's down, up, down. So these are both glucosamines. This is the beta glucosamine. This is the delta, the D-glucosamine. Because they're in ring form, we call it glucosaminopyranose. Okay? Here on the right, bottom right, is a N-acetyl glucosamine in cyclic form, specifically displaying the beta anomer. Again, you can analyze this whole structure by noticing down, up, down means it's coming from glucose. This is up, it's D-glucose. This one is up, means it's beta. And notice there's an acetyl group attached to the nitrogen. N-acetyl glucosaminopyranose is what it should be. Here they're simply simplifying it and calling it N-acetyl glucosamine in cyclic form. Okay, so these N-acetyl sugars appear in different places in biochemistry. They have different functions. So we need to then speak of the oxidation and reduction derivatives that we started to talk about a little while ago. So if you realize, we're going to introduce this. I believe we had talked about this previously, very generally speaking of the oxidation and reduction products of different types of organic molecules. So in this case, we're referring to taking alcohols, whether it's primary, secondary, or tertiary. I'll define what that means in a moment. And then treating them with an oxidizing agent. The most common oxidizing agents contain chromium-6. These are the laboratory reagents. Of course, in biochemistry, it's all done by enzymes. So a primary alcohol, by definition, is an alcohol here that the carbon that that alcohol is bonded to only one carbon. That's what makes it primary. What that also makes it that carbon contains 2 hydrogen atoms. It turns out that for every hydrogen atom contained on a carbon is the number of cycles of oxidation it can undergo. Okay? So because primary alcohols have 2 hydrogens on the carbon to which the alcohol is bonded to, it can be oxidized twice, meaning 2 different levels of oxidation. The first level of oxidation removes one of the hydrogens and adds an additional bond between carbon and oxygen. And that's what's shown here. So aldehydes, when you compare them with a primary alcohol, let me delete this so that you can see it a little bit better. If you compare a primary alcohol to an aldehyde, what you'll notice is that one of the hydrogens has been removed and an additional bond between carbon and oxygen has been produced. So both of those items together, in fact, are oxidation. Remember, oxidation means loss of hydrogen and or gain of bonds to oxygen or total oxygen content. So if you realize an additional bond to oxygen and we've lost a hydrogen. So from an alcohol to an aldehyde, that is an oxidation process. Typically we use a bracket with an O in the middle. Simply, very generally speaking, there's been an oxidation process. So aldehydes are the oxidation products of primary alcohols. However, if you notice, there's still a hydrogen bonded to that carbon. So then an additional layer, an additional oxidation can happen. And if you expose those aldehydes to the same reagent, in fact, if you're using these chromium-6 reagents, you cannot stop the process at the aldehyde. So this forms along the way, but it turns out that the presence of this hydrogen on this carbon adds an additional reaction of oxidation. And then what results is a carboxylic acid. Notice that now there's been an additional oxygen introduced into the structure. What was a CH bond is now a CO bond. The hydrogen is actually now bonded to the oxygen. So this is yet another layer, another level of oxidation. So ultimately, aldehydes will become carboxylic acids. The net result is that really what's happening is that the primary alcohol is ultimately becoming a carboxylic acid. Yes, by way of the aldehyde, you can't stop the reaction at that level. Okay? So what happens if you have a secondary alcohol? Secondary alcohol, if you follow the logic, means that the carbon to which the alcohol is bonded to 2 carbons. It only has 1 hydrogen. So only one level of oxidation can happen. What happens in that level? The hydrogen is removed and then a double bond will be formed between carbon and oxygen. And that's what then produces a ketone, right? A carbonyl in the middle bonded to 2 carbons. The same 2 carbons that were part of the structure, because nothing happens to them. But the CH bond is gone, the OH bond is gone, and a carbon-oxygen double bond has been formed. Now notice, there's no more CH bonds on that structure. It only happens in the alcohol carbon. So you may be asking yourself, what about these carbons that have CH bonds? No, it has to be pertaining to the carbon that has the oxygen on it. Okay, only that one. That's why nothing happens up here with this one. Only this carbon that has the oxygen, because it has 2 hydrogens, 1 and 2 layers or levels of oxidation can happen. In the one down here, this one, there's only 1 CH bond on that alcohol carbon, and therefore only 1 level of oxidation. Notice the ketone has no more CH bonds, so this is the end. Only 1 level of oxidation can happen. A ketone is the product. If you continue with the logic, a tertiary alcohol is the alcohol in which the carbon bonded to the hydroxy is bonded to 1, 2, and 3 carbons. Therefore, notice there's no CH bonds in that structure. I'm talking about the carbon that's bonded to the OH, right? Because there's no such CH bond, then these structures cannot be oxidized. There's no such possibility of oxidation of these compounds. So only primary alcohols and secondary alcohols can be oxidized. Primary alcohols can make aldehydes and ultimately carboxylic acids. Secondary alcohols can only go as far as ketones. Now, this is in the laboratory. These chromium-6 reagents are laboratory reagents. Because biology has the power to do whatever it wants via enzymes. We're going to talk about enzymes in the next chapter. It turns out that enzymes have the power to take it to the aldehyde and stop there. They also have the power to say, well, I want to take it all the way up to the carboxylic acid, and it takes it all the way up. So depending on the enzyme, depending on what the cell wants to do, it can stop halfway because it has that power, or it can go all the way because it has that power. There's nothing more that can be done with ketones, with secondary alcohols. They become ketones, and that's the end, okay? So in laboratory chemistry, it's difficult to stop it, or practically impossible to stop it with these chromium-6 reagents. With secondary alcohols, there's only one outcome. With tertiary alcohols, nothing will happen because there's no CH bond. So, for example, we're going to look later at a reaction when we start talking about metabolism. You probably have heard in other courses of the citric acid cycle, also known as Krebs cycle. So that 10-step pathway, or I think it's 8 steps or 9 steps. It's more than a handful of steps. In that pathway that we're going to learn in detail when we start talking about metabolism, it turns out the second step of that process involves the need to take this compound, which is called citrate. Citrate is the conjugate base of citric acid. Notice how these carboxylic acids have lost their protons. That's why it's the conjugate base. That's why it's called citrate. There's 3 of them. That compound is what gives the pathway its name, needs to be oxidized on this position. That is a necessary step in order for this compound to be able to move forward. However, if you pay attention to that structure, this carbon here in the middle is bonded to 1 carbon, 2 carbons, 3 carbons. That structure cannot be oxidized in that form because it's a tertiary carbon. So what does biology do? Biology says, well, I'm going to solve this problem. It's going to do an isomerization. It's going to move the hydroxy to this position, and it's going to then take one of the hydrogens that's on this position and it's going to put it back on the top. And then notice how you get an alternative structure. We call it isocitrate. It's a isomer of citrate. Now if you look at that structure, this carbon to which the hydroxy is bonded to, let me clean this up, that carbon is now bonded to 1 hydrogen plus the 2 carbons. Because there's now 1 hydrogen on that structure can be oxidized. It's a secondary carbon. Just like the one on the previous slide, the secondary alcohol can be oxidized to a ketone. That original carbon could not be oxidized. So biology will transform structures as needed to allow it to do what it needs and wants to do. But of course, it still needs to follow the rules of chemistry. You cannot oxidize a tertiary alcohol. In order to be able to carry out that oxidation, that is a necessary pre-step before the whole pathway can continue. It needs to do a little bit of a SURU over here in order to produce a carbon that can be oxidized. And until it does that, the pathway cannot proceed. Okay? So it turns out that if you look in biochemistry, we're going to be looking at a multitude of different biochemical pathways as we start moving on to metabolism. Redox reactions are amongst the most important types of reactions. So the question is, would the isocitrate lose the H and then add a double bond? Yes, that is absolutely true. So what happens, not shown here, but what would happen here is that this would then ultimately become, I'm going to attempt to draw the skeleton over here, right? That would become this, right? And then that would be the oxidation step that happens along the path. So when we get to that pathway, we will, if you remember this discussion, right? When we go ultimately talk about citric acid cycle, if you recall this discussion, you will observe that the isocitrate will lose this and it becomes this. And that's the oxidation step that needs to happen in order for the pathway to move forward. Good question. All right. So, as I was saying, redox reactions are amongst the most common and most important transformations that happen as metabolites and substances are taken from either larger entities to smaller things, or even going up the chain, things that you start with that are small and you put the biology takes and starts putting them together to make the larger, much more complex structures. In either direction, redox reactions are amongst the most important transformations that need to happen. So it turns out that because these processes are all carried out by enzymes, the enzyme serves as the vehicle within which the transformation takes place. So biology needs to ensure to the best of its ability that the enzyme itself, which is the orchestrator of everything, is not itself altered or changed during the process. So many of these enzymes that we're going to talk about, particularly redox enzymes, the one involved in redox transformations, they carry an additional component that is incorporated into the enzyme, but it's not part of the structural framework of the enzyme itself. We call those entities coenzymes, as we're going to learn a little bit later. And those coenzymes are appendages, structures, accessories, molecules that will ultimately be the ones that are either oxidized or reduced in the process of the substance of interest becoming oxidized or reduced. Remember, whenever there's an oxidation, there needs to be a reduction to go with it, and vice versa. So if you have a substrate, a substance that's being oxidized, let's say, here's an example of a second alcohol being oxidized to a ketone, the same compound that we just looked at, which is isopropanol, being converted to acetone. Well, if this is being oxidized, I'm going to use the little O over here, something needs to be reduced. It can't be the enzyme, because if the enzyme itself is reduced, you've changed the structure of the enzyme that has the potential to annihilating the enzyme's ability to do its job. So something else needs to be reduced. So these enzymes carry these coenzymes, and this is what then is reduced. For reduction, we typically use a hydrogen in brackets. What that means is that hydrogen has been incorporated. That's sort of the general symbol for reduction. So it says, is the upcoming quiz just on chapter 10 and stereochemistry? You are correct. We're actually going to be cutting off the material for the quiz very soon. I will let you know when it is, but it's not going to involve chapter 12. We'll let you know exactly when the cutoff is. So stay tuned for that. So these redox coenzymes, if the substrate of interest, which in this case is the secondary alcohol, is oxidized, the redox coenzyme is going to be reduced. Oh, and then Delara asked about why does it say 9.3? It turns out that that particular short discussion, let me go back a slide, this discussion over here on structures of alcohols being oxidized is actually coming from chapter 9 in the textbook. You don't really need to go into that chapter. I don't even know that it's part of the chapter list that you had included in your packet. It's not an issue. What you have in the slide is enough for you to get through this discussion. All the information you need is provided in that slide. It just happens to be, there's a much expanded discussion on chapter 9. All right, so back to this. So again, if this is the oxidation process, in this case, the secondary alcohol becomes oxidized, something needs to be reduced. So in this case, it's this structure. We're going to use the little H to represent reduction. So if you compare those two structures, what you will notice, and let me use now a third color, I'm going to use orange. If you pay attention to this position on this structure, and you now pay attention and compare to this position, notice how the one on the right has an additional hydrogen. What does it mean to have an additional hydrogen? That means that that structure has been reduced. Reduction has happened, right? So as the secondary alcohol became oxidized to the ketone, something else was reduced, something else picked up hydrogens, right? So there's two major pairs. They always come in pairs because there's the oxidized form and the reduced form of these coenzymes. Let me write that word again. We're going to come back to it when we talk about enzymes in the next chapter, but they're called coenzymes. And these are these accessory molecules that are contained within the enzymes that they themselves are the ones that get either oxidized or reduced as the enzyme is carrying out the redox transformation. So these processes are actually reversible. A given enzyme, depending on the needs of the cell and what the cell needs to accomplish, can either carry out an oxidation or a reduction. It can go in either direction. And that's where the structure of the coenzyme that it's carrying is critically important. So let me clean this up so that I can point out what I'm talking about. So if the enzyme is going as shown here in this direction, it's taking up some substrate and it's oxidizing it. The coenzyme that's within the enzyme needs to be reduced. So it will exist in its oxidized form. This is the oxidized form of the coenzyme, that upon picking up a proton or a hydrogen, not protons, it's not an acid-base transformation, picking up hydrogen, it becomes reduced. How do I know that that's the reduced form? Because it has one more hydrogen than the one that's on the previous side. So this is the oxidized form of the coenzyme. This is the reduced form of the coenzyme. The coenzyme is referred to as NADH. NADH means that it's the reduced form because it has one more hydrogen. The one that has one less hydrogen, notice NAD, it happens to have a plus charge, that's why it's called NAD+. But notice the difference, one less hydrogen. The one that has one less hydrogen will always be the oxidized form. The one that has one more hydrogen will always be the reduced form of the coenzyme. Okay? So there's a whole bunch of, as I mentioned, oxidized sugars that are out there. And biology, as I mentioned, has the ability to do whatever it wants. So depending on which carbon is oxidized on a sugar is the type of sugar, oxidized sugar, that is produced. So again, we call them oxidized or carboxylic acid sugars. Why? Because either the aldehyde or one of the OH groups is oxidized to oxalic acid. The only type of OH group that can be oxidized to a carboxylic acid is a primary alcohol, if you remember from that previous slide. So it would only be able to happen on the CH2OH that's on one of these. This is a primary alcohol. If any of the secondary alcohols in the structure are oxidized, you will not get a carboxylic acid, you will get a ketone, as we discussed, right? So aldehydes and the primary alcohols are the ones that can be reduced to a, that can be oxidized to a carboxylic acid. So for example, here are two versions of glucose in oxidized form. If you remember, glucose would have an aldehyde on carbon number 1. Notice how here, this has been replaced by a carboxylic acid. So what was an aldehyde, I'm going to attempt to draw it here. Here's the aldehyde of the sugar, carbon number 1. When that aldehyde becomes oxidized on carbon 1, it becomes a carboxylic acid. This is what we call gluconic acid, okay, gluconic acid. The general term for sugars in which their aldehyde on carbon number 1 on the top has been oxidized to a carboxylic acid, they're called aldonic acids. So gluconic acid, galactonic acid, and so forth, those all fall under the umbrella of what we call aldonic acids. The alternative would be the last carbon, the one that was a CH2OH, I'm going to draw it over here, CH2OH getting oxidized to a carboxylic acid, that one is called glucuronic acid. Notice the difference, gluconic on the left, glucuronic on the right. The general name is uronic acids. So glucuronic, galacturonic, and so on and so forth are uronic acids. In the ring form, what ends up happening, let me go back to red color. This OH, if it was the regular sugar, it would have wrapped around and bonded to the aldehyde. Well, guess what? There's no aldehyde anymore. It's now a carboxylic acid. OH comes around and forms a bond now with the carboxylic acid. That of the structure is now different aldehyde, it's a carboxylic acid. What ends up forming is this structure. This is an ester. Okay, if you pay attention, it's an ester. And esters, esters are called cyclic esters. I need to take a sip of my soda. Bear with me one moment. These cyclic esters are called lactose. Okay, this is a general term. So we call that glucuronolactone. Oh my God, I can't even say that. Don't worry about it. It's called the lactone. Cyclic esters. Let me clean this up for a minute. Continue to observe right, oops, left means down, up, down. The CH2OH attacked, notice pointing upward, right? So this is a D sugar. The concept of alpha and beta has disappeared because what forms this OH attacks the carboxylic acid is an ester. This carbon is carbon, and the up-down has disappeared because there's a higher level of oxidation. So all you can say that it's D-glucuronic acid in form, okay? If you look at the one on the right, that's the one where the what CH2OH here is the one that has become oxidized. Well, here it is, right? And because it's upward on the ring, this is the D version of the sugar. And then this one you can speak of the beta version, right? Because this is in the opposite direction. Notice right, left, right, down, up, down. Let me change the color. And this is right. So what that means is that this is pointing. That's what makes the sugar. Okay. If it's last carbon, it's uronic acid, whatever the main frame is, glucuronic, galacturonic. If it's the first carbon, what was the aldehyde, it's onic, aldonic acid, gluconic, galactonic, and so on and so forth. Okay? All right. So, what's here? Did you lose me again? Can people hear me? Lost my connection again. Oh, there we go. It's back. Can you hear me? Can you still hear me? Okay, good, good, good. All right. All right. So let's now put this together with a little bit of what you've been doing in the lab, or what you've done in the lab for hydrates experiment. So you can use this chemistry of aldehydes being oxidizable to carboxylic acids in the lab for diagnostic purposes, okay? So there's a reagent that you learned about in the lab, which is called Benedict's reagent. And what that substance does is that it contains a mixture of different things, but the primary active ingredient, is copper-2 ions. Oops, copper-2 ions. So what happens is that copper-2, in the presence of aldehydes, it doesn't touch primary alcohols, it only reacts with aldehydes, which is perfect because remember, sugars have aldehydes, most of them, the critical ones, glucose and galactose. They also have more alcohols, so they don't, copper-2 does not react with alcohols, it only reacts with the aldehyde. So the components of the mixture, which contains several, as you learned in the videos, it contains carbonate, it contains citrate, and a couple of different things. It turns out the copper-2 will react with aldehyde, it produces a carboxylic acid. It ultimately ends up forming a carboxylate because the conditions of the reagent are actually basic. So it deprotonates the carboxylic acid and produces the carboxylate. Now what happens is that in addition to the carboxylate coming from carboxylic acid, the second product is copper plus 1. And copper plus 1 is the reduction product of copper-2. Copper-2 has a blue color in its solution. It's a very kind of a sky blue color in the videos. And then the moment that that is reduced to copper-1 has a red color. Okay. So depending on how much sugar is in your sample is how much copper 2 gets rid to copper 1. That produces a solution whose color depends on how much of that was converted. If a little bit of the copper 2 converted to copper 1, then you get sort of a bluish green. And as more sugar is contained in the sample, more and more gets converted to copper 1. The color changes bluish green, green to yellow, orangish to a red brick type of a color. So this is very useful in diagnostics. This little card is simply trying to illustrate just with examples of compounds. This has an aldehyde, also has a primary alcohol, only the aldehyde, but not this one converted. Right? Here's one that has aldehyde and a secondary alcohol. Again, notice the acid, the aldehyde is converted to a carboxylate. The alcohol is not touched. Again, always plus copper 1 plus copper 1. And the copper 1, this is what gives you the red-ish color, okay, depending on how much. So again, you can use this for diagnostics as I've been saying. What gets oxidized in the sugar is the aldehyde. So that aldehyde on carbon number 1 is the one that ultimately becomes a carboxylic acid that after losing its proton becomes a carboxylate. In doing so, the copper 2 becomes copper 1. Depending on how much sugar, i.e. aldehyde, is in your sample, is how much of this is produced. Well, what's truly important is how much of the copper 1 is produced. And that's what then can produce your result as being negative if it's still blue, all the way down to a bright orange-ish, reddish color when you have sugar. So we use test strips that we learned in the lab video that they contain multiple things, but there's a specific for measuring how much glucose is in your urine. If you are completely healthy, have no diabetes, it doesn't matter how much sugar you ingest in a meal, you should have little to no of that sugar appearing in your urine. So you should always produce a blue color because none of that copper 2 gets converted to copper 1. If you are starting to develop what we call resistance and then ultimately you're diabetic, then you start producing over time more and more sugar in your urine, and depending on how bad that situation is, you can obtain diagnostic information, and then of course at that point that the clinician would receive that result and then address with further tests accordingly as to what to do with that thing, with that outcome. It turns out that we call these sugars that have these aldehydes, we call them reducing sugars. Why? Because that aldehyde has the ability to reduce the copper 2 to copper 1. Of course, from the perspective of the aldehyde itself, those sugars are becoming oxidized, but they're called reducing sugars because they will reduce the copper 2 to copper 1, and that's what then gives you the positive color change that then is taken in as a positive presence of those compounds in your sample. So it turns out that under the conditions of the Benedict's solution that is basic, ketoses like fructose can actually isomerize. These back and forth arrows means that it can isomerize. And this carbon in fructose turns out to be the second carbon in glucose. There's been a sort of a switcheroo here of the position of the carbonyl. It produces an aldehyde. That chirality center can actually, there's a 50-50 chance that it's in either direction. So of course this one is glucose because it's right, left, right. The alternative version is left, left, right. That one happens to be D-mannose. Doesn't matter which one is produced. What matters at that point is that what was the ketone has become an aldehyde, and both of these can react with the copper 2 to produce copper 1, right? So under the conditions of the test, not only D-glucose, but also D-fructose can ultimately be converted into the corresponding carboxylic acid, which is a glucuronidase acid. So the reason why this is important is that because Benedict's test can also give a positive result with any aldose other than glucose. And the most critical one in diagnostics is galactose. If you have an infant who is lacking an enzyme that is unable to metabolize galactose, we talked about this briefly before, that galactose starts lingering in your body, in the body of the infant. So as the baby is born and starts lactating, that lactose gets broken down into glucose and galactose. The glucose is fine, but the galactose starts appearing in the urine. So the Benedict's test will detect that, and that will allow you to make a diagnosis of what we call galactosemia and ultimately galactosuria, which is, it appears in the urine. And that can then serve as a critically important diagnostic tool to assess and address the issues with these babies, and they have to be treated. They cannot ingest any milk products because that's going to lead to all sorts of issues. Now, if you want to specifically detect glucose and only glucose, there are a series of these strips tests that specifically are targeting glucose because they contain an enzyme that will only metabolize glucose. It's called glucose oxidase. And that enzyme can only recognize glucose, can only react with glucose. So then at that point, if the Benedict test is positive, then you have to decipher, well, does that have fructose? Does it have galactose? Does it have something else other than glucose? Well, let me do the glucose oxidase strip test that will only yield a color change, i.e. a positive result, only with glucose, okay? So there's different levels of testing that you can do depending on what it is that you want to assess. All right, we've talked about oxidation. We also now need to talk about reduction. So as I mentioned, reduction is another important flip side of that. And as I mentioned, aldehydes and ketones can be reduced. In that regard, what was the aldehyde becomes a primary alcohol. What was the ketone becomes a secondary alcohol. So it's sort of the reverse, the exact reverse of the oxidation. So here, for example, is an aldehyde. Notice how it becomes a simple alcohol. Here is a ketone. It becomes a secondary alcohol. So the counterpart of NAD+, which would oxidize the secondary alcohol to the ketone, the converse of that would be taking the reduced form of the coenzyme. These hydrogens would be then incorporated into the carbonyl structures, and that's what then ultimately leads to the reduction of these structures. So the reactions that are shown here in the middle, let me just clarify, these are not biological reactions. Turns out in the laboratory, this is also done industrially for the manufacturing of these sugar alcohols that I was talking about earlier that are used in foodstuffs. If you take aldehydes and ketones and you treat them in the laboratory with elemental hydrogen, H2, elemental hydrogen, typically you need a transition metal as a catalyst to provide a surface where the reaction actually happens. We call that, quite appropriately, catalytic hydrogenation. There's a metal catalyst that accelerates the process of hydrogen being incorporated into these compounds. So it's a hydrogenation reaction, and it's catalyzed by the metal, so it's called catalytic hydrogenation. In biology, the hydrogenating agent, if you will, quote unquote, is again some of these redox coenzymes, of which there's several. NADH has a hydrogen to give. There's actually a cousin of the NADH, for lack of a better word, that has a phosphate in it. It's called NADPH. But notice there's a hydrogen here, that's what that means, that is able to be provided in a reduction, i.e. hydrogenation process. And these coenzymes are critically important in these types of redox transformations. So these reduced sugars that result from this process simply are the ones in which the aldehyde, by the effects of the hydrogen in the presence of the catalyst has become a primary alcohol. So notice that now there's no aldehyde or ketone anywhere on this structure. This is called sorbitol, also called glucitol, because it's derived from glucose. The one on the right, here's ribose. Notice how the aldehyde is now a primary alcohol by way of the hydrogenation conditions. This is called ribitol, right? There's no aldehyde or ketone in these structures. So as I mentioned, if you go to the supermarket, not these days unless you absolutely have to, right? But if you, when we were able to go to the supermarket and all kinds of places and hang out, if you were to pick up a packet of one of these sugar-free cookies, sugar-free this, sugar-free that, for particularly made for diabetics, and if you look at the contents of those, you can also see this in some of the Atkins products, it turns out, you know, because they have low glycemic index. If you look at the contents, you should always look at the contents of what you're buying, right? It turns out if you read, you'll see sorbitol, ribitol, there's another one called a mannitol, right? Let me go back a couple of slides over here where I showed you mannose right here. If you take mannose and you reduce this and you replace that with a CH2OH, you get mannitol. Mannitol. Well, that's another one. Mannitol is used as one of these artificial sweeteners together with sorbitol and ribitol. It turns out mannitol is also used for treatment of certain diseases. Those may end up in a neurology floor. You'll see that it's used to certain neurological conditions, like when there's too much pressure in your head and different, that's a whole other application. But anyway, in terms of the foodstuffs, mannitol, sorbitol, ribitol, it's the reduction products of simple sugars. We call them reduced sugars or alcohol sugars. Artificial sweeteners is the primary application of these compounds. So if you're looking at these structures shown here, glucose on the left, its reduction product sorbitol on the right, here's the aldehyde, here's what then became the primary alcohol. You have two test tubes. One, so test tube here containing glucose, test tube here containing sorbitol. And then you add Benedict's reagent to these tubes, which is going to react. So Benedict reacts only with aldehydes. So of course, the one with the glucose is the one that's going to give you the, let me see if I can do a little bit of an effect here. The one with the glucose is the one that's going to give you the orange color, because that's the one that's going to be positive. However, the one with the sorbitol, there's no aldehyde, that one will remain blue. Nothing will happen. This is a negative result. And how do you know if a reaction has occurred? If you have an orangish, again, remember it can go anywhere from blue-greenish to bluish to reddish to orange, whatever, the whole spectrum, right? Depending on how much glucose is there. But there's a color change heading in that direction, then you clearly have something in there that can react. In this case, glucose. Not specific for glucose. Could have been galactose, could have been fructose under the conditions, which is basic, mannose, variety of different aldoses. We'll do that type of reaction. So now let's look at recognizing the derivatives, right? So what type of derivative is this? So when you stand back and observe, you notice that this is a amino sugar. And if you notice, right, left, carbon 4, this is coming from galactose. So this is galactosamine, okay? And in fact, it's D-galactosamine, because it's an amino sugar coming from galactose. Okay? I hope everybody can see that. Here's another one. So what happens when this structure is reduced to an alcohol sugar, right? So you need to pay attention. This is what's going to be reduced. For the sake of time, we have another 4 minutes. I'm just going to draw what happens to the top. Oop, I screwed that one up. Let me draw this again. So if it's reduced, this is A, this is reduced, so all you're going to get up here is a CH2OH, and the rest of the skeleton remains the same. So this would be A, right? B, if it's oxidized to an aldonic acid, remember the aldonic acid is the one that is reduced at the top, right? So then that would produce a carboxylic acid over here, and then this would be B. This is supposed to be an A over here, right? If it's oxidized to the uronic acid, that's the one, I'm going to do it in blue now. Oops. That's the where this one down here is reduced. So the aldehyde remains the same. I'm going to draw it like this, and then at the very bottom, this down here gets converted to a carboxylic acid. This would be the uronic acid. Okay? So these are reducing sugars. The only one that's going to be reducing is the one that still contains the aldehyde. The manuronic acid will be reducing. And of course, the original mannose is reducing. But the reduced version is not reducing. This one is not reducing. The key for the exam practice problems will go live on Friday so that you have time to do them on your own before before they go live. Okay? All right. Let's, in the couple minutes that we have, let's just do a quick review of let me see how many slides we have left on this. You know what, let's just do, we don't need to draw that one because you're not going to be drawing anything in the exam anyway. You just need to recognize things. So let's just do this question, and I think we can wrap it up here. So if you're looking at this structure on the left, aqueous, which of these sugars on the right, and there's two of them, because one's the alpha, one's the beta, which one represents the aqueous? So if you notice, this is a deoxy sugar. It's missing a hydroxy group on carbon number 3. 1, 2, 3, 4, 5, 6. It's also missing a hydroxy on number 6. So this is a D sugar, right? So that means that this is pointing upward. So all of these are D sugars, so we're all set with that. So again, what does this mean? Left means up, and it's on carbon 2. So this is 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. That hydroxy is to the left on carbon 2. It's going to be up on carbon 2. So up on carbon 2, what happened here? Oops, this is in the wrong place, right? Notice that the hydroxy is missing on 3, which is this one, which is this one. So if you notice, it's these two. Why? Up, nothing, down. Up, nothing, down, which is this going to the right. And then we know that this is D because this, we've already established that. Okay, so again, cleaning it up, this sugar is these two. This one we call the beta. This one we call the alpha. Okay? So that's A. Next time we will continue describing what is a glycosidic bond. Our quiz will go up to this point, not including obviously glycosidic bond because we haven't talked about it. Up to and including this section, up to the slides that I just discussed on aqueous, up to this slide that we didn't get to. We maybe do this next time. Again, you don't have to draw anything on the quiz, but up to and including these slides that recognize the derivatives. Okay? All right, so that's it for today. We will continue on Thursday.